device essentially used to measure heat changes. A bomb calorimeter is a device that is just like think of a giant bowling ball full of water. And in the center of the water is a device, an internal device, that contains, let's say, food of some sort, food. And there's an electric device hooked up into that center apparatus where the food is, where I can actually ignite the food and it will burn, like that, okay? Yes? And what happens is the food burns and raises the temperature of the water. Now, in the next unit, on chapters 21 and 22, part 1, thermodynamics, we'll actually measure how many calories food contains by using examples of a bomb calorimeter. So when you look at a food and you go to the nutritional information and it says how many calories. Calorie is a measure of heat. Joule is a measure of mechanical energy. You can convert from joules to calories, 4.1 joules per calorie, etc. So you can use the bomb calorimeter to determine how many calories a certain quantity of food has. In this particular case, let me read this aloud while you read it to yourself. The caloric value of food is measured with a device called a bomb calorimeter. Oxygen is forced into a sealed container and kept under constant volume. Once the internal pressure inside this container is increased to 150,000, that's what that is, 1.5 times 10 to the 5th pascals is 150,000 pascals. Once the internal pressure is increased to that, a small piece of food inside the calorimeter is ignited with a spark. As the food burns, the temperature inside the sealed vessel rapidly increases from 293 Kelvin to 523 Kelvin. 293 Kelvin is about room temperature, approximately. So you're going from room temperature to 523 Kelvin, which is a lot. A lot. So it says, after this experiment is over, it says, what is the new pressure of the gas inside the chamber when the temperature rises? Okay, so this is the experiment with the bomb calorimeter. It starts off at 150,000. I burn the food, and the food is at room temperature, which is 293 Kelvin, and it burns the food, and the temperature increases to 523 Kelvin. What's the new pressure? The temperature is 523 Kelvin. What's the new pressure? What two things am I comparing? Pressure and temperature. And temperature. What law is that? Pressure and temperature. Gay-Lussac's law. Now, Gay-Lussac was a French physical chemist around the same time as Charles. Charles's law, volume and temperature. Charles died before Gay-Lussac died, and Charles had not published his data on volume versus temperature, but Gay-Lussac did it and gave Charles credit. Gay-Lussac was a really nice guy, and Gay-Lussac's law is credited with pressure and temperature are direct. They are directly proportional. They are proportional. P1 over T1 equals P2 over T2, correct? So this is going to be P1, T1, P2, T2, so let's plug in and calculate, okay? So it's going to be 150,000 I'll leave off the unit labels, make sure everything is in metric, Kelvin. All gas laws has to be in Kelvin for temperature. Pascals, Kelvin, okay? So you're going to calculate and the answer will be in pascals, obviously. So this is going to be over 293 equals P2 over 523. Anybody have an answer for me? What is it? What'd you get?
267,747.
Okay. 200, you want to do that more slowly so I can actually hear you?
267,747.
200.
267, comma 747.4.
Okay. Right, can you read that? Is that off the camera? Let me check real quick. Excuse me, Mike. No, that's fine. Okay. It's close. Okay. So 267,747. Okay. I'm going to rewrite that just in case it's off the screen. Okay, so pressure 2 is 267,747. Is that what I said?
Yeah.
Pascals. And that should make sense. I went from 293 to 523, so the pressure should also increase. Correct? Okay? We'll do one more and then we'll quit. Okay?